Good morning, fifth years. Now, I know I haven't corrected and returned all your tests to you yet, but I did want to give you the solutions so that if you're doing some trig study over the midterm break, you can have these on hand, and I will get those corrections to you as soon as I can. It probably will be over midterm as well. If you are intending on doing the test over midterm, obviously enough, don't watch this video right now because you won't be able to get an accurate picture of your understanding and your assessment. So it's really important that this should only be being watched by people who've already taken the test. So the first question here, 25-mark question, the aim in terms of timing should be to spend half the amount of time, so 12 and a half minutes to answer this. We're asked to complete a table here. They've told us that we've got a function. Now we've started looking at functions, so you know this notation, f of x equal to 3 times sine of 2x. And before we do anything else, let's make little notes for ourselves that this is going to do your range multiplied by 3. So it's going to go up and down 3 times as much. And this is going to do our period, how often it happens, how often the full waveform occurs, divided by 2. Okay, now they want us to complete the table below here. And you'll notice that they've given our domain, our input values in terms of radians. And you can work with them in radians if you want, or we can just put the degrees here just to make it a little bit more accessible. So we've got 180, we've got 90, we've got 45, and we have 135 degrees. 2x then means we're multiplying each of these by 2. Would you be expected to do them in radians? Depends on the marking scheme. So what I might do would be to divide this into 2 pieces. Well, this is going to be the same anyway, so that'll be 0. And in radians, this would be pi over 2. And you can just use your calculator to do that, or 90 degrees. This would be pi, or 180 degrees. This would be 3 pi over 2. Squared, sorry. 3 pi over 2, or 270 degrees. And this would be 2 pi, or 360 degrees. And then you're finding sine of those values. Sine of 0 is 0. Sine of, this is what we're getting, sine of 90 is 1. Sine of 180 is back to 0 again. How do I know? Well, these are our special angles and we should know them. But if we're not sure, you can just put them into the calculator. So sine of 180 is 0. Sine of 270, we're down to minus 1. But if we're not sure, use the calculator. Minus 1. And sine of 360, back to 0 again. So you can use the radian measure, but if you do, just make sure that your calculator is in radian mode if you do that. And then 3 times that, we're multiplying these by 3. So this is 0 still. This is 3, this is 0, this is minus 3, and this is 0. And then they want us to draw the graph of this in the domain. Well, we don't have a million points to plot this, but we know what the shape of a sine graph looks like. In general, sine goes up and down like this, right? So that's the shape that we're going to be expecting to draw. On our y-axis here, we know that we want to go up and down between 3 and minus 3. And we'll use as much space as we can. Do we need to mark in the 1, 2? You don't have to, but you can. And the minus 2 and minus 1. So let's plot the points that we're going to be using. We know that when x is 0, we've got the point 0. When x is pi over 4, we're going to be up at 3. When x is pi over 2, we're going to be back down at 0. When x is 3 pi over 4, we're down at minus 3. And when x is at pi, we're back up here. So if you joined those together in a zigzag shape, you're definitely not going to get your marks, but we know that sine should be a smooth curve. So that's what we're trying to do here, joining the dots in a smooth curve we're graphing the function here, as smooth a curve as we can do. It's okay to have kind of fluffy lines as you're drawing it, and then go over them and make that a little bit clearer when you're done. Okay, so once you've got the basic shape, go over that. You can also erase any of the marks that you used when you were drawing it as well. Okay, so there we go. There's the graph of my function. Now write down the range and the period. So the range is -3 to 3. And the period is how long does it take to complete a full waveform, and that is pi radians or 180 degrees. 360 divided by 2. Okay, so after all the work we did with graphs, I really hope everyone was able to work with that. But if there's part of it you're not sure about, please do let me know. So we had 12.5 minutes to do that, and it took 6 minutes to do it. So it should be doable in the time. Let's look at the next question. Find two values of theta for which tan of theta over 2, now we've had them multiplied before, is equal to -1/3. 0 is less than or equal to pi, which is less than or equal to 4, or is less than or equal to theta, which is less than or equal to 4 pi. This is 720 degrees, 2 full circles. So if you don't like radians, it's okay to change them to degrees to work with. It looks a little bit different to what we've worked with before, but let's just go through the process. We'll have a quick sketch of our unit circle, ASTC, and tan is negative. So there's a minus here. So tan is negative in the second quadrant and the third quadrant. So those are the two that we're going to use. We'll find our reference angle, and that is always tan inverse of this, but you ignore the sign. Tan inverse of 1/√3. So we have tan inverse of 1/√3. Just make sure that your brackets go on right or you'll get an error, and that's 30 degrees. Now they're using radians here, and it doesn't matter. It's fine, you can use degrees. So tan inverse of 1/√3 is 30 degrees, which means that we're talking about theta over 2 here and theta over 2 in here. Okay, so then how do I use it? Well, tan is negative in the second quadrant. So in the second quadrant, theta, but not theta, but theta over 2. Theta over 2 is going to be 180 minus the reference angle. 180 minus 30. So theta over 2 is 150. And then what do we do next? You do your general form before you get rid of that fraction. So the general form is that theta over 2 is 150 plus n times 360, adding on any number of circles. And then we get rid of this 2. Now before we would have been dividing across because we had like 2 theta or 3 theta. Instead we must multiply by 2. So the next step is to multiply by 2 to deal with this 2 that's under the line. If I had 3 under the line, I'd multiply by 3. If I had 16 under the line, I'd multiply by 16. So in general, theta is going to be 300 plus n by 720. So one set of solutions will come from that, or one solution will come from that. Now we must do the fourth quadrant. And the fourth quadrant says that theta over 2, and I'm using theta over 2 because that's what was in my question, is equal to 360 minus my reference angle, minus 30. So theta over 2 is 330. We don't get rid of that fraction yet. We do our general form. So the next step is my general form. Theta over 2 is 330 plus n times 360. This step is always 360 or 2 pi. It changes after you deal with whatever's multiplied by the angle. So the next step then is, again, I'm going to multiply by 2. And just to emphasize, it's times 2 because that's what's under the line. So theta is equal to 660 plus n times 720. If you're more comfortable with that n after the 720, that's fine. There's no difference to that at all. What do we do next? We fill in the two values. So they only wanted two values because we stop at 720. So the first value is when n is equal to 0. We've got theta is equal to 300 plus 0. And also for here, theta is equal to 660. What happens when n is equal to 1? Well, when we try to fill out here, we get a value. We get values greater than 720, so it's out of the range, outside of the allowed values. So technically I didn't even need my general form here because I had it, but you need to be prepared for when this maybe goes to 5,000 degrees or any number of degrees here. So we need to see how far we need to go to get our answers. So those are the answers there. Theta is equal to 300 degrees or 660. You can write them in radian measure. So how do we change them to radian measure? You multiply by pi over 180. So 300 by pi over 180 gives me 5/3 pi, 5 pi over 3. And 660 by pi over 180, and that gives me 11 pi over 3. 11/3 or 11 pi over 3. You will get full marks for your answers in degrees though, because they didn't say give your answers in radians or degrees, which means you have a choice so long as you're clear with what you answer. Excuse me. Okay, again, 12.5 minutes to answer that question. Oh no, there was a part B. It's only about 10 minutes to, only about 5 minutes to answer that really. Now, the diagram here shows OAB, which is a sector of a circle. The radius is 7 centimeters and the center is O. And the angle here is 1.2 radians. So I have to work with radians here. And the area of the shaded region is 21 centimeters squared. So a couple of facts. Remember, the area of a sector is r squared theta. That's in our notes, from the notes, and it's in the log tables as well, when theta is in radians. So I know that fact there. What else do I know? Well, I know the area here. So if I can find out the area, if they want us to find BC, if I can find out this length here, then I can find out that length there. Okay. I don't think I need any of that. Let's use the right-angled triangle that we have here. They threw me off with the area thing. I have a right-angled triangle. I have an angle here. I have this side here. And I want to find this side here, C to O. Why do I want to find that? Because if I know that, then I can work out BC as well. So what do I know? This is my hypotenuse. This is my adjacent. And I can use SOHCAHTOA. I was going down a wrong path for a minute with the area because they sort of led me down a path by talking about area there in the first place. I'm going to use cosine. It's adjacent over hypotenuse. So cosine of 1.2, be careful, radians, is equal to x over 7. The x is on top, so that means x will be 7 times cosine of 1.2 radians. You can go and change the 1.2 radians to degrees. That's probably the easiest way to do this, but let me show you how to do it without changing it. So 1.2 radians, and what do I multiply by? 180 over pi, which is 1.2 pi. So remember, when we're going from degrees to radians, we multiply by pi over 180. When I'm going from radians to degrees, I multiply by 180 over pi. So that will give me 68.75 degrees, approximately. 2 decimal places is enough. So you could use that, or we can change our calculator into radian mode. So on the Casio, shift mode. So you want to get into setup and you press 4, and you'll notice that up here, where it used to be a little d, it's now a little r. So now I can type this into my calculator, 7 by cosine of 1.2, and I will get 2.53. Let's say they said 1 decimal place. We'll go to 2 while we do our calculations. So that is 2.54 centimeters. Okay, let me show you that we'll get the same answer using this. So change our calculator back to degrees. And I can see that it's happened because I have a little d up here. And now I do the same thing, 7 times cosine, but I'm using the degrees, 68.75. And I get 2.53. Slightly different. I had to think a 6 in the third place here, but that's because I've rounded. So I do get the same answer. And then we can do our calculation. So we know this value here. So BC is 7 minus 2.54, which is 4.46, and that it rounds to 4.5 centimeters. That's approximately 4.5 centimeters. If you got 4.4 due to rounding differently to me, that's fine as well. You'll get full marks for that. Okay, so they didn't need us to use the area at all, but they could have done. So this, excuse me, was extra information. We didn't need this. They don't do it very often, but occasionally there's more information in a question than you need. Yeah, okay, so we'll move on. Question 4 had 2 parts. The first one was one of our proofs. Now, we were allowed to use this fact. We were allowed to use cosine of a plus b equal to, I need to look it up actually, so bear with me a second. I don't have my log tables on me. It'll be in our trigonometry notes. So I don't always know them off the top of my head. Especially these ones I do have to look up, just to make sure that I get the signs right. I know that it's going to be a plus b though. Why? Because I'm going to use 2 theta as a plus a. So cosine of a plus b is, I could have guessed because of the minus, but I didn't want to guess, cos a cos b minus sine a sine b. Now, so from there we're going to say, well, this is cosine of 2 theta is going to be cosine of theta plus theta. And that will be cos theta minus sine theta sine theta. And that is cos squared theta minus sine squared theta. Now we're almost all the way there, but we're not quite. So cos squared theta, well, we're going to use this fact. Cos squared theta plus sine squared theta is equal to 1. So we've used this fact. And now we're going to use this fact as well. So this tells me that cos squared theta is equal to 1 minus sine squared theta. What did I do there? I brought the sine squared to the other side. So that means that I can replace the cos squared here, and I've got that this is equal to 1 minus sine squared theta minus sine squared theta again, and that is 1 minus 2 sine squared theta as required. So you'll get most of the marks here for doing this part. If you couldn't spot this last step, that's fine. But I would expect from what we've done with the proofs that you could all do that first step there. If you couldn't, maybe take a note of that and have a think about how you would remember to do a question like that in the future. Now we have a three-dimensional problem here, and they said find the cosine of the acute angle between two diagonals of a cube. What do we know about a cube? All of the lengths of the sides are all the same, so we can call them all x. But you know what? You can make your life even easier. Why not just give them a value? Because of how this is asked, you know it's going to be the same regardless of what value we take for the side of the cube. So suppose we have a cube of side 10. 10 what? Meters, centimeters? It doesn't matter, because we can see that this is going to be the same for any cube. So it's the same for any cube. Then, excuse me, we want to find the angle in between two of these lines. So let's look for our right-angled triangles to start with. Remember, in three-dimensional problems, we're always going to be looking for our right-angled triangles. So here's one going through, and here's one down here. Let's label some of our vertices. Let's call this A, B, C. The one back there can be D. And I'll draw out this right-angled triangle, A, B, C. I've got this right-angled triangle out here. And what am I trying to do? I want to find this length here, because then I can find this length here, and I know that half of that, I'll get a triangle here. So BC, I'm calling it 10. AB, I'm calling it 10. And by Pythagoras' theorem, I know that this will be 10 root 2. That was a big jump without doing any calculations. Well, when they're isosceles right-angled triangles, it's always going to be root 2. 10 squared plus 10 squared is equal to my hypotenuse squared. So you can see where the root 2 is coming from here. That will be the square root of 200. And if you put that into your calculator, or that's root 2 by root 100, so it's 10 root 2 equal to my hypotenuse. You don't have to do the calculation, you can actually learn that off. So now when I draw out, say, A, B, C, D, E, F, G, H. So let's look at this triangle. Another right-angled triangle, C, G, and then all the way over to A. Now I know that this is 10 root 2, and this is 10, so I can find this diagonal here. And again, by Pythagoras' theorem, we've got that this hypotenuse, h squared, is 10 squared plus 10 root 2 squared. So it's a little bit more complicated. So that ends up being 300, and h is going to be 10 times the square root of 3, 10 root 3. 10 root 3 there. So this is this diagonal here that we're talking about. So finally, this is the triangle that I want to look at. We could have done this with x's, but it just gets way more complicated. Because this must be true regardless of what cube we pick, and I'm going to draw it around like this with my angle up here. So I'm doing GC down on the bottom, GC, so that's 10. and I'm going to the midpoint here. So let's call that O. Well, what is this distance and this distance? It's half of that diagonal, which is 5 root 3. So I have 5 root 3 here, and I have 5 root 3 here. So now I can use my cosine rule to find that angle in between there. So remember, our cosine rule says that a squared is equal to b squared plus c squared minus 2bc cos of the angle in between. And we can rearrange this, or I suggested that you learn off that cosine of a is going to be b squared plus c squared minus a squared divided by 2bc. A, B, C are my little sides there, and there's my angle in between. So cosine of the angle, which is what we were asked for, we're asked to just find cosine of it, is going to be b squared 5 root 3 squared plus c squared 5 root 3 squared minus a squared minus 10 squared all over 2 by 5 root 3 by 5 root 3. And this is a good bit harder than I had thought about when I assigned it, guys. So we have 5 root 3 all squared plus 5 root 3 all squared minus 10 squared, which we know is 100. You can fill it in straight away if you want to, by twice 5 root 3. And again, if you want to do some of the calculations before you type them into your calculator, that's fine as well. 5 root 3. Okay, so it's going to look something like that when you've typed it all into your calculator. And we get a third. And that's the answer. So cosine of that angle is a third. There are other ways of doing this, but this is probably the easiest way to do it. Okay, I do expect that most people probably got a bit stuck on that question. If you got it out, fantastic, well done. I'll give you some more comments on that once I see the work that you've done. Just remember, attempting it, identifying right angle triangles, that's going to give you a lot of marks in this question, even if you can't do any calculations with it. So attempting to identify the triangles, breaking down the right angle triangles first, and showing how you might work with those will give you a lot of marks in a question like this. Okay, so let me just lift this up so you can see the whole thing in one go, if you're wanting to take it down. Okay, thank you.